Hello. Good morning. It's a little early for those of us who came from the West Coast or for other time zones, so thank you for all being here. This is JSConf. If you're not sure, if you're not supposed to be in JSConf, please leave now. There's the door. You still have time to get out before we unleash the drones. Too late. So I am Dead Program. In the real world, my name is Ron Evans, but that's not very important right now. I'm the ringleader of Hybrid Group. So this other guy here is Adi Zankic, also known as Adrian Zankic in the real world. But most interestingly, he's the serious programming guy at Hybrid Group. So that means he does all the work and I take all the credit, which is nice. That's a joke. Or is it? Well, we'll discuss that later at the bar.
Exactly.
So we're with the Hybrid Group. We're a software development company based in Los Angeles, California, home of the flying space robots. That is not a joke. If you're a fan of either the Jet Propulsion Laboratory or SpaceX, you know I'm not actually making this up. We're also the creators of Kids Ruby, which is an award-winning free and open source tool to teach kids programming. But that's not very important. We're here to talk about JavaScript robotics. This is Maria. I thought it was Electra, but I was confusing my mythologies. Maria, she's the leader of a robot proletarian revolution, but that's a whole separate talk. Let's talk about that the future is already here, but it's not very evenly distributed. At least that's what the author and futurist William Gibson said. And it's really true, isn't it? When was the last time you went to an Apple store? You can buy drones there. You can even buy robots at Best Buy. There is a lot of amazing hardware happening, but the software has not really kept up with the hardware. Even though you can buy all these cool and interesting devices, there's no easy way to hook them all up to do something useful. That's why we created Cylon.js. Cylon.js is a JavaScript framework for robotics, physical computing, and the Internet of Things, or as I like to call it, the real world web, except that doesn't flow off the tongue. So it supports multiple hardware devices, different hardware devices, and multiple different hardware devices at the same time. So cool. This is all thanks to the amazing concurrency that we can have via Node.js and the V8 engine. So Cylon.js makes programming devices as easy as web development. Well, you're going, web development easy? Yes, it is really easy compared to the sad old days of the 90s when we all used Gopher. Thank you. Thank you for the history buffs. So programming devices has just been really too hard, and so Cylon.js is a framework designed to make that as easy as web applications are today. So it has a built-in API, because of course without an API you can't program your internets over the intertubes, and that's no good. You need robotic internet-controlled devices, right? It has test-driven robotics built in. We think this is really important. I know that some people claim TDD is dead. I think they're a little confused. If Toyota, for example, yes, I own a Prius. If Toyota had only used test-driven robotics as part of their brake system, just imagine if GE or GM, GM with their ignition system. I mean, there's a lot of examples where people do hardware-based development and their idea of testing is flip on the switch and then step back, hoping that it doesn't bite you on the way. It's kind of dangerous. So test-driven robotics. And the command line interface, because CLI is the new API. You don't want to be using GUI tools to program your devices or to get them started. You want to be able to use a command line interface to do all the normal things that you would do. In fact, we have a name for this. We call it Robot Ops. It's DevOps for robotics. And we have a whole separate website for this at robotops.com. Our CLI is actually a separate set of tools from our robotics framework. It's called Gort. You can check that out at gort.io. So gort.io for the CLI tools, robotops.com for DevOps for robotics. But let's get to the actual demo. You guys ready to see some real robotic devices? Yeah. Oh, hell yeah. So we're going to start with the canonical microcontroller, the Arduino. So the Arduino is a very, very simple microcontroller. You can buy them everywhere. Radio Shack even sells them. Yes, the Shack is back. If you need parts, go there. So here's a very simple example of a Cylon program. So the first thing we do is we say var Cylon requires Cylon, which, as everybody here probably uses Node, is how you bring in the main Cylon module. Then we declare our robot. Cylon has a declarative syntax as opposed to an imperative one. So you define the things that you're going to use, and then they just work. So we say our Cylon robot has a connection to an Arduino using the Fermata adapter on port dev TTY ACM0, which if you're using Linux is your default serial port. So we have a single connection. Then we have a single device, which is this LED, which is using the LED driver on pin 13. And then the work that we're going to do. The work that we're going to do is every 1 second, we're going to my.led.toggle, which will cause the LED to flash on and off. And then last, we tell the robot to start up. So we see here the 3 important conceptual ideas behind Cylon.js. The first one is connections, which are using the adapter pattern, which is a software design pattern, similar to the way that object relational mappers allow you to use different kinds of database back-end engines without changing your code. Cylon.js allows you to use hardware devices, different hardware devices, but using the same code by changing the adapter. And then the driver, we're using the double adapter pattern. So we have adapters for our connections, and then we have separate ones for drivers. So the code for an LED is exactly the same whether you're running it on a BeagleBone Black or a Raspberry Pi or an Arduino. So here's our some video. And so we have here the Arduino, and it's plugged into the largest LED that we could find conveniently. And so when Adrian runs the code here, it's going to be communicating using the serial interface. And yes, it is blinking. Gratuitous applause. Applause for a $2,500 lamp. So it's using the Fermata protocol, which is running on the microcontroller itself. This is the same way that Johnny 5 and a lot of other similar robotics tools work. It's actually communicating from the computer to the microcontroller via a serial interface. So let's look at another device, the Tessel. Who here has heard of the Tessel? All right. So Tessel is a JavaScript-powered microcontroller. You actually run JavaScript that's been compiled into Lua on the device itself. So we brought one of those. Let's take a look at the code. The code looks almost exactly the same as the Arduino. Okay, once again, we declare Cylon. We say our Cylon robot. This time the connection is to a Tessel, using the Tessel adapter, but otherwise it's exactly the same. We're still using the LED device. The work that we're doing is exactly the same. Every 1 second, we're going to my.led.toggle. So not everyone has actually had a chance to look at one of these little guys. Yeah. They're, I believe, shipping on Monday. That's what the email said. So this is the Tessel. It's plugged into exactly the same breadboard with the same LED. You know, because we're trying to save money. Also, you know, mercury, lead, there's a lot of nasty chemicals in your electronics. Don't just throw them into trash. Properly recycle them. All right, moving on. So we're going to run the exact same code. And this time, however, we're going to compile the Cylon code, and it's going to execute right on the Tessel itself. So example 1, we were on the computer talking to a microcontroller. Example 2 with the Tessel, we're going to do the exact same thing. And yes, Tessel blink. Okay, so now we're down to a much more reasonably cost flashing lamp.
Yeah, just so you know, the previous example with the Arduino, my computer was communicating to the Arduino through the serial interface. This one, the code is actually running on the board itself. So with Cylon.js, you can actually write your firmware that runs on this microcontroller itself. So you don't need a computer at all for this. So the only reason why I'm plugged into this is for power. So if I had a battery pack or something, this could be completely isolated somewhere with the firmware running, written in Cylon.js somewhere, doing something. Controlling some LED somewhere.
Exactly. Somewhere in the world, an LED is blinking. All right, so now let's move on to the BeagleBone Black. So the BeagleBone Black is a single board system-on-chip Linux microcomputer. It's very similar to a Raspberry Pi, but better. If better is defined as more processor, more memory, and more capabilities. So the BeagleBone Black, we have Cylon.js running on there. Let's look at the code. Should look exactly like the code you've already seen, right? In this case, once again, requires Cylon. We're making a connection, this time using the BeagleBone adapter. And once again, the same, our friend, the LED driver, but we named the pin a little differently. In Cylon.js, we have mappings so that whatever is labeled on the board is what you use in your code. So no more looking through data sheets trying to figure out the mysteries of naming, and it turns out this one is 43, but that one's actually P2_12, or in this case, P9_12. So we make it a lot easier for you to just look at how it's labeled, write the code the same way, plug it in, and it should just work. Let's just take a quick look. Here is, again, the Tessel code. Here is the Arduino code. So Arduino code, Tessel code, BeagleBone Black code. Same basic code, just with little tiny tweaks. You see a pattern starting to form? All right. So let's take a little look at the BeagleBone. It looks very much like all these boards tend to look. It's a surface mount components with some headers. The BeagleBone Black has, I believe, 68 digital I/O lines that can be used for general purpose I/O, for analog, for I2C, which a lot of devices like LCDs and accelerometers and other things use. And so Adrian is going to, well, tell us what you're going to do.
Allow me to explain. So we have Node.js running on this BeagleBone Black. So this computer, this is actually a full-fledged ARM-based Linux computer. So these two previous examples, this Arduino is a microcontroller that we are communicating with over a serial interface, remotely controlling the pins. This Tessel is a microcontroller that runs JavaScript directly on the board, so this has no operating system, just running pure code. This is a full Linux computer, which we're writing a Cylon program that runs on the computer. So, you know, it's 3 different use cases for how you control pins and that sort of thing. So let's run this program really quick.
He's SSH'd in, and so he's actually executing the code on the BeagleBone Black itself, or he would be if it had run. This is how you know it's real.
And it blinks.
Yes! All right. Hello. I'm going to do a karaoke song. No, just kidding. All right. So this is the perfect time for the Choose Your Own Hardware Adventure. Yes, choose your own hardware adventure, because we came provisioned with all sorts of awesome gear from our wonderful friends, in case you're wondering how we got so much of it. So this is your opportunity to get some of this. So to win a Sphero 2.0, just go on the Twitterverse and tweet Go Sphero and Cylon.js. Okay, so Go Sphero and Cylon.js if you want to win a Sphero 2.0. If you want to win a Pebble smartwatch, tweet Pebble and Cylon.js. And if you want to win a BeagleBone Black, tweet BeagleBoard.org. Kind of long. BeagleBoard.org and Cylon.js. So those Twitter names again. To win a Sphero, tweet Go Sphero and Cylon.js. To win a Pebble, tweet Pebble and Cylon.js. Or to win a BeagleBone Black, tweet BeagleBoard.org and Cylon.js. All right, on with the show. Sphero plus Leap Motion. All right, so a bunch of people have seen the Sphero. It's a very cool, we call it the minimum viable robot. It is a toy. It looks like a toy. It is, in fact, a toy. But it does have a few interesting characteristics. One of them, it has input. It has a built-in accelerometer, so we can detect collisions. The other is that it has 2 different forms of output. One is that it can roll around. It has a built-in accelerometer, as I mentioned, so it can auto-stabilize the same way as a Segway or a MIP or some other kinds of robotic devices. And it can change the color of its built-in RGB LED. So let's take a look. The code here is a little bit more complicated. We could see now an example of using 2 different devices at the same time. So we have 2 connections. We have the Leap Motion connection and then the Sphero connection. So the Leap Motion The Leap Motion is a gestural controller that plugs directly into your computer and then allows you, through its built-in camera and infrared projector, to figure out where your hands are positioned and use those as a way, without any wires at all, to control some kind of device. So it puts out its data via WebSockets, and so you can see here's the port that's running on. Then the Sphero, it's a Bluetooth device, but we're using a Bluetooth to serial connection. So again, our old friend, in this case, it's RFCOM0, which is the typical port used by Linux. Again, if you're doing robotics and you're not using Linux, you're probably doing it wrong, but that's a whole nother rant. So then we have two devices, the Leap Motion and the Sphero. Then the work that we're going to do, we're going to turn on the tail light of the Sphero so we can tell which way it is pointing, or pointing away from. Then here is our event syntax. It looks exactly like the kind of event syntax that you've seen as a Node developer, because in fact it is. So on my.leapmotion.onHand, we grab that data from the hand and we scale it using some of our built-in scaling functions, since you have to do a lot of scaling when you're moving from, for example, the Leap Motion to a servo or something of that sort. So we scale the hand X and Y coordinates to something that the Sphero can use. Then every 1 second, we're going to roll the Sphero, we're going to set the color to a random color. Then every 0.01 seconds, we're going to look at that data from the Leap Motion and decide which direction to roll around in. The reason we have to do this is we need some way to manage the concurrency. The Leap Motion puts out data a lot faster because you can wave your hands very quickly and it can detect that a lot more quickly than the physical device can respond, in this case, the Sphero. And then last, we Cylon.start. So let's go back to my camera. So this way we can kind of see both his hand. So he's waving his hand. Okay, that's better. Look, Ma, just a hand. This is really fun. By the way, we have a table in the makerspace area, along with the NodeBots team and the Node Rockets team and a bunch of other cool people. So if you are wandering around and you're bored of the hallway track and you just don't have the attention span, come on in there. We have lots of parts, and you can play with this stuff. We have a Leap Motion that each person can use, but you can't keep them, or else we're going to get in big trouble. All right. So Sphero plus Robo. So we're going to show something completely different now with the Sphero. Who here knows Conway's Game of Life? All right, so only a few mathemagical people. So a brief description. So there was this guy named John Conway. Not John Connor, that's a fictional character. John Conway. John Conway, a man completely obsessed with mathemagic. Specifically, he keeps looking at these flocks of seagulls, and he knows seagulls are not especially intelligent, and yet they fly in these amazing formations. He can't stop thinking about it, like all mathematicians. And he sits down with a piece of paper and thinks really hard and solves a problem. And that problem becomes a whole new field of mathematics that we call cellular automata, or more popularly, artificial life. So he makes this game, known popularly as Conway's Game of Life, and it's normally played on graph paper, which I highly recommend you go out and get a pad of graph paper, because it's an amazing tool for creativity. All good ideas start on graph paper. You don't have to stay within the lines. You can just know they're there, and it makes you feel nice. All right, so Conway's Game of Life, these little circles are cells, and the squares are an absence of cells. So each one of them follows the same basic set of 3 rules. So the first rule is, if you are a cell and you have less than 2 neighbors, you die because of loneliness. If you have exactly 2 other neighbors, then a new cell is born into an empty square. And if you have 3 neighbors, then you die from overpopulation. So with these same basic 3 sets of rules, you go through each one of the squares, and depending on whether it has a cell or not, you apply these rules. So first move would look like this, and the second one would look like this. So we thought it'd be really cool to create Conway's Game of Life, but with robots. Just take anything in the universe and add with robots and see what it does. It's kind of fun. So, but we realized there were going to be a few changes we'd have to make. First of all, we don't have a really fast 3D printer that can create new Spheros on the fly, in case you're wondering how we get new ones to be born. We're working on that. Also, they have no eyes. They can only detect collisions by way of the built-in accelerometer. So because we are alpha mathematicians, we use something called an inverse Fourier transform, which basically allows us to take a slice of time, and then using the number of collisions we detect within that slice of time, we create a number which corresponds to the approximate number of neighbors. All right, you guys got that? Cool, moving on. So here's the code. So what we're going to do is we're going to run 5 Spheros, which we've named Thelma, Louise, Grace, Ada, and Mary. That Mary is supposed to be Missy, which stands for Missy Cummings, first female fighter pilot in the United States Navy and an associate professor of human-machine interfaces at, I believe, Duke. Anyway, so each one of these Spheros is going to be running the exact same code. So let's see what that code is. So our Conway robot, we have a connection and a device, which we're going to fill in the port number when we start them all up. Then they're born. When they're born, we set the number of contacts and age to 0. They have life and they have movement. So when they move around in a random direction. That's a little bit different. There is no randomness in the original Conway game, but we're very random people. So we thought it'd be fun. So when they come to life, they are alive and they turn green. When they die, they stop moving and they turn red. If they have enough contacts, then they can stay alive. So when one of these robots has its birthday, we tell it happy birthday. If it has enough contacts and it's not alive, meaning already dead, it comes back to life. Zombie mode. Zombie robots. It's real. Otherwise, they die if they don't have enough contacts. And so then the work that we do is we connect, start detecting collisions, we detect them, and we keep this counter. Every 3 seconds, we move if we're still alive. Every 10 seconds, we have a birthday. So life is hard, short, and spherical in Spheroland. And then we're going to start out for each one of the bots that we declared initially in that first array. We're going to go through, and we're going to say, here's a new Conway robot. We're going to tell it which port and what name it has, and then we're going to start it out. And then this line here, we're going to turn on Cylon.js's built-in API. It has an express.js API built right in, and we also have a single-page web app built using AngularJS called Robo. So similar to the way your router has an admin page that's just built right in, we have Robo built right into all of the Cylon.js code that you write. That way you can test to see, well, in my case, my code is not working, but why? That's the interesting question. We can go in and we can use Robo to figure that out. So first of all, let's... Is the router still on? It says it's on. We brought our own Wi-Fi. Something to do with not trusting conference Wi-Fi. Can't imagine. You got disconnected. You didn't pay your AT&T bill. Yeah, it says it's my Wi-Fi. Oh, I didn't pay my bill. Oh, Well, let's... Oh, now it's back on. Oh. Well, we saw the AT&T cell tower here. It's in a truck that's parked kind of on the back 40. This is not a joke. We can show it to you later if you don't believe us. If you want cellular signal, just kind of point and don't move. All right. He's going to connect. You'll know that they're connected because they stop flashing. They take on a sustained color. Standing by. They're thinking. Think, 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 think. Just imagine when you're in orbit and you're waiting. Like, we're waiting, Houston. We're standing by. Yeah, exactly. 45 minutes later when you ping Mars and you're, it didn't work. 45 minutes later, you ping Mars again. That's weird. It worked this time. All right, well, 4 out of 5. All right, they're rolling around. They're looking for love in all the wrong places. They need to collide with each other. Actually, with anything. Some people have said, how do you tell when they only collide with each other and not the walls? Well, a wall is a Sphero to a Sphero. It's going to restart it really quick. Okay. Okay. Standing by. The Death Star explodes. That's a very interesting question. He asked, when does the Death Star explode? That brings up the question, was it contractor failure? Or were they partisans who inserted a design flaw intentionally? We could discuss this at the bar later. But I'm original trilogy for life. Keep that in mind. Almost there. All right, we're going to go to the next demo if you don't get it this time. I'm getting bored. I mean, I don't got all day. So little to do, so much time. Wait, strike that, reverse it. Yes. No, not that. That one didn't count. Do not look at the Sphero behind the curtain. Is this not running? Something's not going. All right, I'm ready to move on to the next demo. Well, they're not playing well with each other, actually. Yeah. We have nothing to do with this game. There is no human robot yet. All right, so let's move on to the next demo. If you want to see the Conway's Game of Life with Spheros, come find us in the hackerspace. All right, let's get into some drones. Because since we didn't have the Spheros working, not having the drones working will be so much more interesting. So we have support for the AR drone, thanks to the hard work of the Nodecopter team, which we wrap around like many of the libraries we use. If you hadn't noticed, we support all the same hardware, plus a lot more. It's because we are standing on the shoulders of giants, not on their toes. So we're going to show an AR drone with OpenCV, a PS3 controller, and a NeuroSky. So what is this all about? So the AR drone, it's the popular Parrot AR drone that if you've been to a Nodecopter, you've already flown. We're going to be using OpenCV, which is an open source computer vision package that is very, very commonly used for things like facial recognition or edge detection. We're going to fly it around with a PS3 controller, which we're using, I believe we're using a library that was partly created by Andrew Nesbitt. And then we're going to use the NeuroSky brainwave reader. We're not going to fly the drone with the brain. That would not be a very good idea because most people do not have enough brain control to even fly without a brain controller. Instead, we're going to monitor the brain waves of our pilot. And if he gets really nervous, we'll know. All right, so put that on here. Let's take a look at some code while he's getting ready. So once again, var Cylon requires Cylon. That's how everything starts out. And then we dynamically include the modules that are needed for whatever hardware you're using. In this case, we're using 3 connections. We have a connection to OpenCV. We have a connection to the DualShock 3 joystick. And we have a connection to the AR drone itself. Then we have 4 devices. The first one is the Matrix. Not the Matrix you're thinking of. This is the Matrix that's used by OpenCV for its optical recognition. Then after that, we have the window so that we can actually see what the drone sees. We have the controller for the DualShock 3, and then we have the drone itself, Flight Commander, so we can control it. So we have a little helper to validate our pitch so we don't flip over. Then the work that we're going to do is we're going to grab the data, and we're going to show it on the screen. Okay, so every time we get a new PNG file from the camera, we're going to display it inside of the window. Then based on the different controllers, we're going to either take off. If you press the square, if you press the triangle, we'll hover. If you press X, we'll land, etc. Then every 0, so if you ever use set interval, you probably wondered at its API because it's really confusing. We didn't like it, so we wrote our own little helper around it. Every 0 does something as quick as it can, but asynchronously. So every 0, we're going to grab the joystick info, and then based on whether you put it left, right, turning, or pitch or yaw, we're going to change those. Then in similar fashion, we're going to do the same thing for the rotation. And then if we lose control, we're going to hover. Then here's the code for the NeuroSky headset. We're running another little separate Cylon program. We're just grabbing the NeuroSky data, and then we're going to log it. So let's see if this works here. Oh, wait, I got to run my code. Okay, there's Adrian's brain on JavaScript. So we could tell if he's getting really nervous. The door is right there. Under the tables works. The battery life of the AR drone is maybe 7 to 12 minutes of full flight. Good to know, right? And this way we can kind of see. Now we really are standing by. Standing by. Standing by. Yeah, everyone turn off your Wi-Fi. Just kidding. Thinking. Working. 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 Aha. Let's go see what his brain has been doing this whole time. Looks kind of erratic, bro. So now you're trying to decide, should I watch the drone or watch his brain? There is a lot of interference. In your brain or the drone? If it crashes into you, we're really sorry. All right, so Cylon, PS3, AR drone, and NeuroSky. Whew. No humans were injured. All right, we have one last demo, and then we got to get out of here because there's a lot of other cool people doing a lot of other cool things. So now we're going to show you the mother of all demos. We're going to show you a Pebble watch that's featuring R2, controlling an AR drone with OpenCV, doing facial recognition, then controlling some Spheros and the DigiSpark running on the drone itself. In other words, R2, well, let's explain very briefly. So what is R2? R2 is the same idea as Cylon.js, but it's written in Ruby. We call it Ruby on robots because we love many languages. So we're going to use R2 communicating with a Pebble smartwatch. Here's the code. Same exact idea as what you saw. We don't have time to go through the whole thing, but it's the same basic idea of what you already saw, but in Ruby. Same design, software architectural design pattern. In this case, we're going to detect when the button pushes, and then we're going to start the whole thing off using the API. All right? So then we're going to communicate with our drone running Cylon.js. In this case, we're going to be doing the facial recognition part, so that's why we need the matrix again. So we're going to look at your face, and if it's recognized based on the generic human face, so any human will work. Basically, when we detect that face, if we detect a face, we're going to send an API command to another microcontroller that's running on the drone itself. So we have a very, very small little USB-powered microcontroller called the DigiSpark, which is plugged into the USB port that's on the AR drone. And we have this LED plugged into the top of it, attached via either electrical or duct tape, depending on what was available. So when it detects that, it's going to send a command that we're going to flash the LED on the top of the drone. So when it's looking at a human and it detects it, the LED will start to blink. The Spheros will start to go crazy. and you will be able to see a green outline around the human face through our universal video adapter. And so we're actually running code on the AR drone itself. It's actually a single board Linux computer of its own, and we're using GoBot, which is our Go language framework. So we have R2 is going to tell the Cylons to command GoBot if everything goes well. And here's some Go code. If you haven't looked at Go, this is the Go code that we're running on the AR drone itself. That's basically, it's that same blink that you saw before, but now implemented in Go and communicating with the DigiSpark. All right, so now. He's waking them up. Everything all at once in one massive demo. What could go wrong? Nothing could go wrong, especially if you're sitting in the back, you're pretty safe. Yeah, normally we choose a volunteer / test subject / target. But now that we can start it all off through the Pebble, that means he gets to be both the serious programmer and human subject. Oh, human subject. It sounds really nice. You've got humanity. You are the point of the whole thing. How can you complain? It's all about you, man. How many devices can we use all at once? We could probably add a few more, but we don't have enough time. In fact, we're losing devices rapidly. Device attrition. You start out with like 40 and you end up with 3. There can only be one. Think. All right, let's do this. Do you need me to increase the screen size when it runs? Okay. All right, so you get in front of the drone. You get between me and the drone. All right. There it goes. Where's the video? There it is. Oh, ooh, it spotted somebody else behind you. Quick, throw yourself between him and it. So you see the light on top is flashing every time that you see the green square, because when it recognizes a face, friendly or otherwise, there's too many humans in this room. All right, the mother of all robotics demos. Was that fun? Did you guys have fun? Did you enjoy that? I certainly did. Thank you. So join the robot evolution, not revolution. Those usually don't work, but evolution seems to work fairly well given our current status. So join us, Cylon.js.com or Cylon.js on Twitter, R2.io or R2.io on Twitter if you prefer Ruby, GoBot.io or GoBot.io if you would like to explore the exciting world of concurrency in the Go programming language. Thank you very much.